This is a recording for notes for pre-calculus, section 2.6. It's called rational functions. So until now, we've looked at polynomial functions, which are kind of have those smooth curves and things like this. And now we're going to look at rational functions, which could be written in fractional form. And so like, our basic fraction function is like 1 over x. And if you remember, 1 over x has asymptotes at the x-axis and the y-axis. And so we have some familiarity with asymptotes, but I do have this little reminder, and maybe it's a reminder more to me than you based on your familiarity. But if you have a horizontal asymptote or a slant asymptote, they deal with only end behaviors, so the graph can cross a horizontal or a slant asymptote. A graph of a function can never cross a vertical asymptote as we go. And so just kind of keep that in mind. And I put it right at the heading here as a kind of constant reminder for us. So our objectives are to find domains of rational functions and find the vertical and horizontal asymptotes. We'll have some rules for that. And the graphs of rational functions, to be able to sketch the graphs of rational functions, and kind of keep in mind we're not allowed to use a graphing calculator for an exam anymore, but we can use that as a tool to kind of help us, and we can use the features, the table features on our calculator. But we're going to try to find some key values and kind of look at properties related to these functions. Then we want to not only sketch the graphs of rational functions, we want to sketch the graphs of rational functions that have slant asymptotes, and then of course use rational functions to model and solve real life problems. So in this section, just to give you a forewarning, early on in these making of these slides, I had to be gone for a few days. So this is a section where I kind of have things very laid out and underlined because I was gone. And so I made maybe not even recordings. I can't remember back that far. And but I have some pre-written things on here, and I feel like they're good enough that I've kind of left them on there. So I will go through the slides, but some of my work is kind of pre-done on here as we go. And so just to let you know, the first subheading is our introduction. And so that's why it says like write underlined information. Maybe I wasn't recording lessons back when I first did this. So a rational function is a quotient of polynomial functions, and it can be written as f of x equals n of x over d of x. And just a reminder, when we're talking about fractions, the top of the fraction is the numerator and the bottom of the fraction is the denominator. And so possibly that's why the book authors use n of x and d of x. And so those are polynomials, and d of x is not a zero polynomial, because if it were, then things would be undefined for us, and that would not be good. So in general, the domain of the rational function includes all the x values that are real numbers except x values that make the denominator equal to 0. So much of the discussion of rational functions will focus on their graphical behavior near the x values excluded from the domain. So we're going to focus on kind of those points. And, I don't have that underlined or highlighted, but you might also underline or highlight this part that says the domain of a rational function is usually all real numbers except x values that make the denominator equal to 0. And so that is something kind of that we want to keep in mind and be able to look at. So in this first one, and I already kind of commented about 1 over x, so we're going to do like a little just looking at observing the function 1 over x, f of x equals 1 over x. It is a function, and we're going to discuss the behavior of it near any excluded values of x. So we'll just kind of go through this, and first we'll just find the domain. So let me kind of slide that up a little bit. Make sure you write that this is 1 over x that we're looking at. F of x is 1 over x. And so I'm just going to remind myself f of x equals 1 over x. And it's undefined when x equals 0, because that would make the denominator equal to 0. Is undefined when x equals 0. So the domain, if we give that, can be written one of these two ways. In set builder notation, the domain is the set of all x such that x does not equal 0, comma, and x is an element of the real numbers. Oh gosh, sorry. Is an element of the real numbers, or in interval notation will come from negative infinity to 0, 0 to infinity, excluding 0. So, right, or negative infinity to 0, parentheses for everything, union with 0 to positive infinity. And so that's our domain. And then it also tells us to discuss the behavior of f near any excluded x values. So this isn't like an English, dissertation or paper about what the behavior is like. It's a mathematical discussion. So what we want to do to discuss this mathematically is we want to give ourselves some data and kind of look at what happens when we're very near 0, that undefined term. And so the way that we're going to do that is we're going to make a table of values. And if you were in math analysis, you've done this kind of work before. So I'm going to try to keep everything a little bit, I was going to try to keep it a little close there, but I don't think I can. So I'm going to make a big XY value table, and kind of in the middle here, so I'm going to work from the middle out. I don't know if that's a great idea or not, but I want to look at things that are super close to 0. I'll go negative first, and just kind of see what I can look at. So when I want to be super close, I'll look at negative 0.001. And that was a little hard for me to write. I'll look at negative 0.01. That's a little bigger, I guess, or further away. I'll look at negative 0.1, and I'll look at negative 0.5, and I'll look at negative 1. So, that's just what I'm picking to look at. We just generally want to look at things that get closer and closer to that 0, and then I'll do the same thing in the positive direction. So I'll look at positive 0.001, that's really close. And I could use more zeros if I wanted. I'm going to look at 0.01. I'm going to look at 0.1. I'm going to look at 0.05. Oh, just kidding. Oh, I am not going to look at those. I see on a table that I had previously made that I'm going 0.01, and then I'm going to go 0.05. I don't know. I must have found a time that was important to me, and then I'll go 0.1. And so I'm not using the exact same positive as negative values, but I want to get that closer value look at that. So take a moment, pause this. Use your calculator because you want to just be familiar with that too. Use the calculator you're allowed to use, which is not a graphing calculator, and find some values for those as you go, and we'll kind of just see what happens as we look at that. Okay, and let's see how we did on this. Now, like I said, I have this from from before, so I'm actually going to use that information and I'll go through that with you. We already answered all this, and you can see I wrote things out very well because I was evidently gone. So if you want to read over that, and this is kind of making that table, and then let's look at what happens. And if you have a little space above and below that table, you might write some of these things as well. So the values that we got should be like -1, -2, -10, -100, -1,000. So I'm going to read what it says in blue here. Look at what happens to the y values as x gets close to 0 from the left. So I'll use my yellow marker right now. So x is getting closer to 0 from the left side of 0. And notice that these y values are decreasing without bound. So f of x, which is the other name we give y, f of x goes to -infinity. So as this goes to 0 from the left, and so sometimes we're going to put a little negative there from the left side, then the y values, or f of x, is going to -infinity. And then look at this green information here, and I don't have in the 0.1, but I think it was 10. I think I had that written someplace. You can correct me if I was wrong, but I think it was 10. Oh gosh, it is. I wasn't thinking about what it actually is. So in green it says, look what happens to y values as x gets close to 0 from the right. So if we're coming from the right, we're getting close to 0 from the positive side. And, right, we're going to put a plus sign, left, we're going to put a negative sign. And then look what's happening. We have 0, 10, 100, 1,000. Notice that the y values are going to +infinity. So y is f of x again, and that's going to +infinity as we look at that. So you decide what you want to write to kind of have a good sense of this, and you can do a comparable table for other values as well. And it's not always going to be negative and positive. Imagine for a moment if this, instead of 0, was like 15. I don't know. And then we would go, 15.001, 14.999 or something like that. So just some things to go by. And then look at what I have written in black. That's what we want to kind of write as our part of our discussion. So this is a mathematical discussion we're giving. So we use a table of values. That's going to give us some data. And then we're going to write a few more things. And so this black is good information. It's a little more drawn out. In blue below here, I'll have it a little bit more symbol oriented. So here it is. As x approaches 0 from the left, 0 with a little negative above it, f of x decreases without bound, so it goes to -infinity. And as x approaches 0 from the right, 0 with a little plus, f of x increases without bound, so goes to +infinity. You decide how much of this you're writing out as we look at this, and I will just read through. So this, I think, would be good information to have as well. And that could be your discussion along with that table of values. So the table of values, the black writing is kind of just a little more wordy, just so that you can understand it better. But this says, and remember, we always say what's happening to y as something happens to x. So we kind of write it in that reverse order. If you write it like the black stuff writing, that's absolutely fine. But here's kind of the bottom line. F of x goes to -infinity as x goes to 0 from the negative side or from the left, and f of x goes to +infinity as x goes to 0 from the positive side or the right. This means that the line x equals 0 is a vertical asymptote. Also notice from the graph that y equals 0 is a horizontal asymptote. And so maybe take a moment and do a nice sketch of this graph of 1 over x. And then I'm going to move on. So pause this if you need to see that longer. Now we're going to talk about vertical and horizontal asymptotes. You maybe have some familiarity with that already. We want to just get a firmer grasp of these asymptotes as we go. In example 1, the behavior near x equals 0 is denoted as follows. We already have kind of written that down. The line x equals 0 is a vertical asymptote. And I'm just going to tell you on this book author's, in the printed book and these slides as well, they do not actually show an asymptote if it is on an axis. So just be aware of that the asymptotes are there, even though if they're on the axis, this book does not kind of print those in, so to speak. So we also know it has a horizontal asymptote, and then, that's just going to be the information of what happens as f gets near y equals 0. And you can read through that as well. Then moving on, I have this a little pre-highlighted, so I've just left all that on there. So this is definitions of vertical and horizontal asymptotes. So the line x equals a is a vertical asymptote. And so, I don't have anything vertical written in here, but you might draw in a little vertical asymptote. Oh, I should have maybe drawn it as dashed vertical asymptote. And of the graph of f when f of x goes to infinity or f of x goes to negative infinity as x goes to a, either from the right or from the left. And so that's going to be a vertical asymptote. The line y equals b is a horizontal asymptote if the graph of f when f of x goes to b as x goes to negative infinity or positive infinity or negative infinity. Notice here I have written in blue, this is about end behavior. So a horizontal asymptote may be crossed near the y-axis. And if you've noticed, I've said that several times already. The reason is I know that you will have to know that as well. And so here's the deal. Eventually, as x goes to positive infinity or x goes to negative infinity, the distance between the horizontal asymptote and the points on the graph must approach 0. And so they kind of get close to that as we look at that. I'm going to go on to the next slide, so if you need to write something down, go ahead. This is a nice little picture, and you can either look at it or pause this and write things down. But just to kind of graphically or visually look at it, if we were together, I would be asking you some questions, so I'll just kind of comment on the things that I would say. Here is the rule for each of these. Kind of look at those, and the vertical asymptote here is at x equals -1. The horizontal one is at y equals 2. Maybe think about why that would be as you look at that. And these asymptotes I have drawn in red because you can't see them. This one has no vertical asymptote, but it has a horizontal asymptote at y equals 0. As we kind of look at that. And then this one has a vertical asymptote at x equals 1. And think about why that would be, and a horizontal asymptote at y equals 0. So, I would maybe ask more about that, but think about in this one, and I'm going to get rid of all my yellow for the moment, and then kind of write it back in. Oh, I have a lot of yellow there. Oops. Let me go back to that. Okay, so notice if this denominator was equal to 0, we'd get x equals -1. Oh, look at that. That's where that one is. And I'll skip over here. If we let this denominator equal 0, we would get x equals +1 because we would square root each side, and x minus 1 would still equal 0, so x would equal +1. But look at this one. Notice if I take that denominator and set it equal to 0, well, if I do that, x squared would equal -1, and that would just mean that x would be, plus or minus I, and so it's not a real answer as we go. And then, maybe just think about any thoughts about the relationship between these rules and those horizontal asymptotes. And, I'm maybe not going to comment on that. I'll just let you look at it and see. Then for this next one, the graph of 1 over x and this other one, 2x plus 1 over x plus 1 are hyperbolas. And we'll be talking about hyperbolas in the spring, just to kind of let you know, but this is your first, word hyperbola as we go, and we will have to know some things about that. And so my comment here is you should have at least one of these in your notes labeled as a hyperbola. And for that number 1 problem, we have 1 over x already. So, in my opinion, we maybe have that done already. So good job for us. But label it as a hyperbola. Moving on. This is kind of how to determine these asymptotes, and I do have some notes written on here for myself. This is a little slide you want to write some good information about and kind of come back to it, but ultimately you want to kind of have a sense of this in your head by the end of the unit when we take the exam, the next exam. So I'm just going to go through it right now. Vertical and horizontal asymptotes of a rational function. Let f be the rational function, f of x equals n of x over d of x. And there's the whole thing, and written probably in absolutely in descending powers, degrees, and where n of x and d of x have no common factors. So there's no common factors to cancel out. One says the graph of f has vertical asymptotes when d of x equals 0. So you just set the bottom equal to 0, find what x values make that equal to 0, and those are where the vertical asymptotes will be, if it's in simplified form. And then number 2 is the graph of f has 1 or no horizontal asymptotes determined by comparing the degrees of the top and the bottom. So I'll read what it says in print, and then I'll read my blue writing to kind of justify how I think of it in my head. When n is less than m, and just a little note to self, it's a little hard to see up here, but n is the degree of the top and m is the degree of the bottom functions or polynomial functions. The graph of f has the line y equals 0, the x-axis, as a horizontal asymptote. When n equals m, the graph of f has the line a sub n over b sub m. And so notice those are the coefficients of those first terms, the leading coefficients as we look at that. The ratio of the leading coefficients as a horizontal asymptote. And when n is greater than m, excuse me, the graph of f has no horizontal asymptotes. So in blue, I have written down, and this is how I think of it. If it's x to a lower power over x to a higher power, the asymptote will be at y equals 0. If it's a sub n x to the same over b sub m x to the same, so whatever those are, then y equals a sub n over b sub m, kind of the leading term over the leading, or leading coefficient, excuse me, over the leading coefficient. And then if it's, excuse me, x to the higher over x to the lower, then there's no horizontal asymptote. So that's kind of what I look at as I go. And there is an important point here that it said it has no common factors, because if they do have common factors, we have other things happening besides asymptotes. And yes, it's going to be a hole in the graph, so just be cautious there as you go. My voice is a little unsteady right now. So let's look at a problem and see what happens. This is 2. There's an A and a B for this. It says find all of the vertical and horizontal asymptotes of the graph of each rational function. And so write that down. And I'm just going to start going through this. One thing I would do is possibly, and you're going to find it's going to be helpful as you go through problems, one thing you want to do is actually have both the original and maybe a factored version of the original. Both of those will give you information you'll want to know. So this is 2x squared over x squared minus 1. Oops, I wanted to factor that really because you've written that down already probably. X squared minus 1, to get x squared I need x and x. Minus 1 is minus 1 and plus 1. So I have this factored, and vertical asymptotes, I'll kind of color code this. Vertical asymptotes are going to be when the denominator, we're going to set the denominator equal to 0. And I'll just write den equals 0. Denominator equal to 0. So x minus 1 times x plus 1 equals 0. So this is x equals positive 1. This is x equals negative 1. So that's where the asymptotes are. The vertical asymptotes are in those spots, so to speak. And then the next one is horizontal asymptotes. Horizontal asymptotes. And so for the horizontal asymptotes, we want to look at this version and kind of see what's happening. For this, we're looking at the powers here and here. And notice that they're the same. So I have 2x to the same over 1x to the same. And so when that happens, then our horizontal asymptote is going to be y equals 2 over 1, or just y equals 2. The coefficients of each of those leading terms as we go. So then what does that look like graphically? They didn't ask you to do that. We're done with this for the book authors, but in our future, we have to be able to do more with that. So if this is my axes, and I'll just maybe do a little better job. If these are my axes, and 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, not super well drawn, but if I want to draw in my vertical asymptotes, oops, and let me go back here, and my vertical asymptotes are at x equals 1 and x equals negative 1 and x equals 1. My horizontal asymptote, I'll color code them just because I am, but I would maybe draw them the same color, is at y equals 2. So that's what's happening there. Here's 2b. If you want to try that yourself, go ahead, pause this and see what happens, and then I'll go over it with you. Okay, let's see what happens here in this one. Well, like before, I factored that first for myself, but notice here that the x plus 1 or plus 2's are going to cancel out, and so then we're going to end up with x minus 1 over x minus 3. And if you look back at that box that we wrote notes from, it says they have to be in reduced form to kind of find the vertical asymptotes. And so for the vertical asymptotes, we know the denominator has to equal 0, so x minus 3 equals 0. So we get a vertical asymptote at x equals 3. For the horizontal asymptote, the degrees are the same, and so we get y equals 1, the coefficients of each of those as we go. So if we wanted to graph this and kind of look at where they were, there's our vertical asymptote and our horizontal asymptote. The question is, though, that this one kind of still has unanswered right at the moment, is what about this value that has let me get a kind of different color. What about the value when x equals 2? This is our original rule. If we put, or excuse me, when x equals -2. If we put -2 in, there's still going to be an issue. It's going to be undefined when we put in -2. So what is happening when it's -2? And we'll discuss this later, but when x equals -2, it's still undefined. Undefined. Sorry, bad writing there. It's undefined, and what we'll find happens, and I don't know exactly where it'll be on here, but we'll have a hole someplace. There will be a hole in our graph, which is just going to be some kind of little opening that has an undefined value but doesn't have an asymptote at that point. So then our next one is let me find it here. Oh, wait. By setting the denominator of the simplified equation equal to 0, you can determine, oh, okay, I don't know why I kept that slide in there. So here's the next one. Try this before we move on to doing some problems together, and then I'll go over it at the beginning of this next part. So this concludes 2-6 notes, part 1.